Hi everyone, I'm Shengtuo, a PhD student from University of Michigan. Today I will present our recent work on automated discovery of denial of service vulnerabilities in connected vehicle protocols. This is a collaboration work with Professor Chen from the ASGuard Research Group at UC Irvine, and Professor Yiheng Feng now is an assistant professor at Purdue University, Professor Henry Liu from University of Michigan, my lab mate Jiachen, and my advisor Professor Morley. The connected vehicle technology has been brought out for years. In general, CV technology wirelessly connects vehicles and infrastructures together to share vehicle status and services in real time. It aims at enhancing the safety, mobility, and convenience. As shown in this figure, signals from the responder vehicle inform oncoming vehicles of a crash ahead. It warns drivers of lane closings and that they should reduce speeds when approaching the incident zone. However, the integrated communication capability vertically increases the attack surface of vehicles. Since CV technology will be closely connected to our daily life, it's highly desirable to systematically understand design-level flaws in the current CV network stack, as well as in CV applications, and the corresponding security consequences. We mainly target potential design flaws in the CV network stack and CV applications, because design flaws can affect all implementation. Solving them can help us proactively address the security problems before large-scale deployment to avoid unnecessary costs. Among different security properties, we identified that availability is a missing piece in the CV security analysis. CV technology brings us different services to enhance driving safety. If the services are not available, the benefits of CV technology no longer exist. Therefore, it's quite important for us to guarantee the availability of CV communication. In this graph, the attacker can disable signature verification such that all incoming threats warnings will be discarded and never reach to the driver. Before starting the security analysis, here is a list of limitations of existing works. First, there are lack of systematic approaches for attack discovery and threat assessment and rely on manual efforts. Second, they pay less attention to the availability threats. Third, they target on prior generations of protocols, ignoring the analysis of CV applications. Overall, make 4 major contributions in this work. First, we performed the first security analysis on CV protocols, including the latest version of IEEE 1609 protocol family and 2 platoon management protocols. Second, we showed the effectiveness of CVAnalyzer and find multiple new denial of service attacks. Third, to show its practicality, we validate all of them in the real-world testbed. At last, we also discuss fundamental reasons and propose mitigation solutions. For the security analysis, we follow the same threat model as recent works. We assume that the attacker can fully control a CV device and own valid certificates. Therefore, the attacker can send arbitrary packets to surrounding vehicles and passively eavesdrop all packets from others. We do not consider any attacks against the crypto operations. In other words, the attacker cannot break existing crypto algorithms. Here is the overview of CVAnalyzer, a model checking-based approach. CVAnalyzer combines the general model checker for vulnerability discovery and the probabilistic model checker for result assessment. There are 4 steps within our approach: model construction, model checking to find counterexamples, result assessment to quantify consequences of identified attacks, and attack validation. We will briefly introduce all 4 steps in the later slides. The constructed model includes 2 components: protocol state machine and the environment. For the state machine, we manually extract the model from specifications for CV network protocols or from code bases for 2 platoon management protocols. We consider both packet type and packet data in our model. The environment handles different events: incoming, outgoing packets, added, deleted, expired timers. The state machine will first retrieve an event from the environment and process it. Then it may generate new events and deliver them to the environment, which is the post-processing step. We place the attacker with the environment so that the attacker can inject arbitrary packets to the environment and monitors all transmitted packets. As we mentioned before, we consider packet data that usually has large data domain, which largely increase the total number of states for model checking. Therefore, we propose a state reduction approach to eliminate to eliminate unnecessary states while still preserving soundness. Our goal is to ensure that the counterexample found in the abstracted model is still a valid counterexample in the original model. As indicated in the formula, if the identified counterexample violates property hat, which is a weakened property in the abstracted model, it will also violate the original property and thus is a valid counterexample in the original model. Our state reduction approach is built upon two observations. First, without the attacker, not all state transitions will be triggered. Therefore, we only keep a small set of them. Second, different attack inputs trigger the same state transitions. Thus, we can reduce attack input space as long as the attacker can trigger all unique state transitions. After building the model and applying a state reduction approach, we combine two different types of model checkers. For the general model checker, we choose TLC due to its expressiveness of constructing the model. We formulate the availability property as a liveness property. Here is a high-level property we used. We want to ensure that the application layer can always consume valid incoming packets. We further refine this property for different protocols. By analyzing the generated counterexample, we can formulate the attack procedure and analyze the fundamental reasons for identified attacks, which is helpful for mitigation design. Then we use a probabilistic model checker prism for risk assessment. Unlike the general model checker, PMC assigns probabilities for each state transition. In our paper, we assign uniform probabilities to concurrent state transitions. With probability information, PMC can help us generate quantitative results like attack success rate and verify time-related properties. We only use PMC to quantify the severity of non-deterministic attacks, which are defined as attacks that may not always succeed per attempt. This is a summary of our findings. From the general model checker, we successfully identified 4 new denial of service vulnerabilities in CV network protocols and 15 attacks in platoon management protocols. We also showed in our paper that some of them can eliminate the benefits of CV technology and further resulting in traffic collision. Due to the time limit, we will only introduce one attack, N3 here. This is the pipeline of P2P-CD, which stands for peer-to-peer certificate distribution. It's a unique feature specified in CV security services with the goal of helping a CV device to learn unknown certificates. In CV network, all packets are required to be signed and transmitted with a digital signature, which form the secured protocol data units, SPDUs. If the signing certificate in the received SPDU is unknown to the CV device, it will record the unknown certificate and send a learning request to invoke P2P-CD procedure. By design, once a peer device that knows the requested certificate observes the request, a learning response will send to the network. Then the CV device can store the received certificates for future verification. The attack goal of N3 is to prevent victim device from sending learning requests. According to the protocol specification, if a CV device observes a learning request to the same unknown certificate, it will discard its own request and wait for responses from others. If the attacker sends a learning request, the victim device will not send its own. However, due to the broadcast nature, the learning request from the attacker can still be received by a peer device. To achieve the attack goal, the attacker further exports unicast of CV communication and only transmits the learning request to the intended victim. In this case, the attacker can further block all future steps in the P2P-CD pipeline. The CV device will not be able to learn unknown certificates. Therefore, it cannot consume packets from peer devices. We leverage PMC to quantify the severity of non-deterministic attacks from N1 to N4. We observe that P2P-CD attacks can succeed only if malicious packets are delivered to the victim vehicle exactly within the attack time window. However, the attacker cannot precisely infer the start and end of the time window. Then we use PMC to quantify the severity based on success rate and time delay. As shown in this table, all 4 attacks can achieve around 99% success rate. For the time delay, 218 milliseconds is the one-time delay introduced by P2P-CD itself. At the worst case, they can even double the time delay. To show the practicality of identified attacks, we validate all of them in the real-world testbed, which consists of 3 OBUs, Two of them are victim CV device and one is the attack device. During the attack validation, we also find some implementation details that makes our attacks easier. For example, we found that N1 and N2 can indefinitely block the CV communication instead of within a specific time period. We also demonstrate the attack impacts of identified attacks. For example, PPCD attacks can eliminate the benefits of CV safety applications, leading to rear-end collision. The audience can refer to our paper for more details. To defend against identified attacks, we have detailed discussion of fundamental reasons in the paper and further propose mitigation solutions as listed in this table. PDP-CD attacks from N1 to N4 are mainly due to the optional verification of learning responses, truncated hash, and the unicast feature defined in CV network protocols. Solution 1, 2, 3 together can defeat N1 to N4. For PMP attacks, they are mainly caused by the missing error recovery mechanisms, which should not be ignored by future CV applications. At last, to conclude this presentation, we performed the first rigorous security analysis to find denial-of-service attacks in CV network protocols and applications. We discovered 4 new attacks in PDP-CD and 14 new PMP attacks, eliminating the benefits of CV technology. We demonstrate the practicality of identified vulnerabilities. As well, we discuss the fundamental reasons and propose mitigation solutions. Thanks, everyone. I'm open to any questions.